Alright, what's going on, you guys? Another LeetCode video today. This problem's called Palindrome Partitioning. So we're given a string S, and they want us to partition S such that every substring of the partition is a palindrome. And then they want us to return all possible configurations, or all possible palindrome partitionings of S. So basically, yeah, they just want us to partition S in as many valid configurations where every partitioning of S is a palindrome. So we can see in this first example, they give us this string S, it's AAB, and there's only two ways you can partition this string into its palindrome substrings, right? So either you can always separate each character individually, right? Because a single character is going to be a palindrome. And by the way, a palindrome is just a string that reads the same forwards as backwards. This other configuration here, we can see the just A together is the same forwards and the same backwards. So that's the other configuration of palindromes. So so let's get into the whiteboarding for this problem. The way we're going to solve this is with recursive backtracking. So let's work with that first example they gave us. So it was A, B. So for our first, so for seeding our recursion, we're going to want to have an index to tell us where to start looping at each point in our recursion, because we're going to want to loop through this string. We're also going to have just an empty vector here, which will contain all of the partitions. Eventually, we want this to be full of partitions of this entire string, with each partition being a valid palindrome before we can add it to our result vector of vectors that have those strings, right? So the first thing we're going to do is just, and then let me specify. So this is going to be an index, right? This is where we start looping pretty much. Okay, so I is going to be 1 at first, because we're going to increment I from wherever we are in our loop for the next recursive call. So I is going to be 1 here. And when I is 1, or I is actually going to be 0 here, because we're actually looking at I and this step of this part of the recursive tree, right? So, and okay, so I is going to be 0, and we're going to basically just loop from I to the size of this string. So we're also going to have J, and J will be 0. So we're just going to be considering this part of the string, right? So if this is a palindrome, then we can add it, and it is, we can add it to this vector of strings, right? So we'll just have an A in here at first. Okay, and then for the backtracking, we're going to have another call from this part of the recursion, right, where we backtrack, which basically means we're going to remove this partition that we just added. By the way, I is going to be incremented as well, because, or this index, right, it would have been 1 here, so now it'll be 2. And we're just going to try, so we're going to increment J, right? 0 is the same for this part of the recursion, but I gets incremented. But J gets incremented. So J is going to be 2 now. So what does that mean? We're now considering, or what I say was before 0. So it's gonna be 1. So now we're considering 0 and 1, right? So it's gonna be AA. So is this a palindrome? Yes, it is. So we're gonna add it to this vector. Like that. Okay, and then finally we have to increment j one more time before we can't anymore, right? J can't be 3, but it can still be 2. So we would go this way, and so our index now that we're starting at is going to be 3, and now we're considering this. Is this a palindrome? This is obviously not a palindrome. So I'm gonna show what that would look like if we tried to add it, but we're not actually gonna add it because it's not a palindrome, but this is what that would look like. Obviously not a palindrome, so we wouldn't add that. Okay, so that's it for that level of the recursion. So let's go down, let's proceed to the next level. So 1 is gonna be, it's gonna get incremented, right, that index. We're definitely gonna have this A already in here. So we're gonna be considering, so I is gonna be 1, right, at this level of the recursion. So I is gonna be 1, and because right now we're considering this node. And then J is going to be 1 as well at first. So we're just going to be considering this character here. That is a palindrome, so let's go ahead and add that. Okay, and then let's backtrack for and then do the next call. So our index here is going to be 3. We're going to backtrack off that A. And now whereas I is still going to be 1, but J is going to be 2. So we're just considering this part of the string, right? So this is not a palindrome, so we're not going to add that. And that's what that invalid partitioning looks like. So we're getting rid of this. And we can't increment this index anymore, so that's it for this node. So let's go to this node now. So I is going to be starting at 2 from this node. So that's where we're going to start looping. So going this way, we have that index gets incremented, and then we're going to bring down this double A, and now, so J is going to be 2 at first, so index 2 is just this B, index I through index J is just 2, 2, so we have the B. That is a palindrome, so let's add that, and notice, so that was this is a valid configuration, and this index has reached the 3, so we can't increment it anymore. So this is going to be, that's how we know this is going to be part of our answer, right? So this is one possible configuration of palindrome partitionings of AAB. So yeah, we can't increment this index anymore, so that's it for this node. So the only one left to do is this node here. So we're going to increment that index to 3, bring down the vector of strings that we have so far. It's just this A and the A. So J is going to be 2, or I is going to be 2 rather, and then J is just going to be 2 as well. So again, we're just considering that B, and that's obviously a palindrome. So let's go ahead and add it. And same conditions as before, we can see this 3 has reached the size of AAB, and this is a valid configuration so far, so we're going to add it to our answer. So in terms of the time and space complexity, really what we're searching for in this recursion is it's just it's basically all the possible subset configurations of AAB. So and to expand on that, so say we have that string AAB, you can either cut the string or not cut it in between every character, and that's going to give us 4 different possibilities here. So you could either have AAB all separated, you could have it none of them separated, or just the first or just the last, right? So like this and like this. So what that works out to in combinatorics is it's going to be basically the number of ways we can separate this, just disregarding whether they're palindromes or not. It's going to be 2 to the n minus 1, right? So because n here equals 3, and then the number of combos here is 4, right? So that would be like 2 to the 3 minus 1, which is 2, so that's 4, right? So so a better estimate for that for a big O notation is just going to be, for the time complexity, is just big O of 2 to the n, right, for every possible combination there. But also we're going to have to, so that's like for every every possible partitioning, but we also need to check if each partition is a palindrome, and that's a linear operation. So it's going to be 2 to the n times n for the time complexity. And then for the space complexity, it's just going to be big O of, let's see, it's just going to be big O of n, because the deepest, and that's for the recursive, the space for the recursive stack, because the deepest path you can have in the tree is what you look for the recursive space complexity. And the deepest path is only going to be, you can only add 1 character minimum, or that's the least amount you can add, right? And then that'll give you a path that's got the greatest depth possible of just n, which is the length of the string you're partitioning. So yes, let's get into the code for this problem. So we are going to first need just a vector of strings for the result. I'll just call it res for short. We also want a vector of strings for the current partition. I'll just call that par. So I'll just do a function overload for the depth for search on partition, and then we'll return those results at the end. So let's go ahead and write. So we're going to need 2 private functions, right? The first one we need is just a function that can, in linear time, check if a string or if a subsection of a string is a palindrome, right? So we're going to take this string by const reference. So we'll say const string s, and then we just need some pointers to a left and a right index of the substring that we want to check in that string to see if it's a palindrome. So we're going to just do, we'll say while left is less than right. So while the left index is less than the right index, we're just going to compare at each character. So if the string at the left index doesn't equal the string at the right index, we're going to return false, because that means the string can't be a palindrome, or the substring at that point in the string cannot be a palindrome, so we can just return false immediately. Otherwise, we increment those indices and then keep checking. If we get all the way through, if we scan from the edges of the string to the middle and it's all of the characters line up, then we can just return true, because it's definitely going to be a palindrome. So that's it for this function, and then let me just outline. So the time complexity is going to just be big O of n, right, linear, and then space for this is just constant. So yeah, so let's go ahead and get into the recursive backtracking. So we'll overload partition. That'll just have a void return value. It's going to take some parameters, so we want that index, right, to know where we're going to need to start looping. We're also going to need the string s. That can just be by reference. That way we're not copying it unnecessarily. We also need the current partition. So that's just a vector of strings. And that, of course, can also be by reference. And then finally, the result vector of strings for all of the possible partitions. So that will also be by reference. Okay, so let's go ahead and see this first. So I will be 0 at first. The string we're using is just the one they give us in the function parameter for partition. And then we pass in par, and then which is the, just the current partition we're trying to build in a given path, and then result is all of our results globally. So the first thing we want to check is we want to see if I has reached the length of this string s, because when it has, we basically know that we've built a valid palindrome partitioning, just the way we're structuring our code. So indicates that to us. So we're going to use res.pushback on the current partitioning just to add that to all of our results, and then we're going to return to indicate we don't want to do any more. We don't want to change this partition anymore, right? We're done with this path. So now we're just going to loop from the starting index that is given to us, so from I to the length of the string s. So I'll use j as our iterator, index iterator. So j will be equal to I, and then while j is less than s dot length, we increment j. And then we just ask, first we need to check if the palindrome, in the range we're considering, or if the substring in the range we're considering is a palindrome, then we can potentially, we will add it to the current path and then see if we can form a partitioning moving forward. So we'll say is palindrome, and then we pass in s, and then the pointers are going to be, the left pointer will be I, and the right pointer will be j, right? Just the way we made this function. Okay, so if it is a palindrome, then we can, on par, we'll push back that substring to this current partitioning, right? So the way we're going to do that is we'll use the substring method on string. The first parameter is going to be the index of the substring we want to start at. So that's always going to be I, and then the second parameter is the number of characters that your substring contains. So the way we're going to determine that is just take j minus I plus 1. And the reason is because, say we're at, say I is 1 and j is 2, right? So basically we would want to take the substring, say we had, say our string was a, b, well, we'd want the substring from a to b. So a, b is the substring we'd want. So how do we get that? Well, the first index we have to get is I equals 1, right? And then there's going to be 2. The substring is going to be of length 2. So to get 2 characters, we just take j minus I, which is 1, and then we have to add 1 because the last index is, these pointers are literally on the indices, right? So if we want to get the proper string length, we have to increment it by 1. But nevertheless, yeah, hopefully that explanation helps this, because this is a little can be a little confusing. So that's how we're going to get the substring, and then we're going to just call our recursion right after that. So partition on j+1, we're going to take the value of j, increment it, and then we'll take the same string, the current partitioning, and then the results. And then after that, we have to do backtracking, right? Because this is a backtracking problem, and we did do backtracking in our this whole algorithm kind of relies on backtracking. So we're gonna have to pop back after that and then try the next available substring, pretty much next available candidate, right? So yeah, so that's pretty much it for this code. Let's go ahead and submit this. And hopefully this video helped you understand the problem better for, what is this called? Palindrome partitioning. Yeah. So hopefully this video helps you understand palindrome partitioning better. If it does, leave a like and subscribe. I'll see you guys in the next video. Peace.